Ah, hello everyone. Hello, hello. I hope that we are all doing well today. Welcome, welcome, welcome. Welcome. I can articulate properly. Hello, Asterotovos. I'm so glad you got your dummies. And now I don't actually know if I'm pronouncing that right, but yeah, it's awesome. I got mine too, so I'm very, very happy about it. I've also acquired a shiny Diglett in Pokemon Go. So the odds are currently in my favor. Not that I really needed the shiny Diglett, but more shinies are generally welcome. Pretty much always welcome, really. All right. So let's see. Let's get rolling. Today, we are talking about the paired samples test, also known as the repeated measures t-test, also known as the dependent means t-test. Uh, and there's probably more names for it out there. I actually don't really know what to call it. I think it might be called the dependent means t-test the most often. I've gotten in the bad habit of calling it the repeated measures t-test, which I would argue is a perfectly valid name for it. Ooh, shiny Skidoo, nice. I want to go back to playing Pokemon Violet and stuff, but yeah, my freaking carpal tunnel does not play well with Nintendo Switch at all. Like, Nintendo Switch is the single worst thing I can do for my carpal tunnel, it seems like, which sucks. I'm so sad. I want to play all of the Pokemon forever. I would play just I don't play many video games, but the ones I do. Worse than Wii? I haven't actually played Wii in a long time. I should boot it up though. I recently finished Fate Extella Link. Like I'm a big fan of Muso games. I say a big fan. I haven't played that many, but I love Muso games. And one of my favorite Muso series is Sengoku Basara. And the most recent game in that series that I'm aware of that's been released in the US is on the Wii. So if I want to play it, I need to boot up my Wii, and I hope that it hasn't been so long that it just died on me, because I have not booted up that Wii in like a decade. I hope it's still functional, because I really want to play Basara. Oh. Anyway, putting aside my horrible gaming habits and my even worse wrists, let us talk about this t-test of many names. So like, what was it? Last Wednesday, we talked about the one sample t-test, which is like you have one sample and you're comparing it to a population or like some sort of like benchmark number. Then on Monday, we talked about the independent measures t-test, which is you have two independent groups. You've got an between subjects design, two independent groups, you're comparing them. This case, this is what happens when you have two conditions or two time points or whatever you want to call it that are not independent. This is a repeated measures design or a within subjects design, and that's why I call it the repeated measures t-test, because it's a repeated measures design. But yeah, lots of names for this one. Lots of names for this one. But first, we get to do a little bit of review. Also, I'm trying the lowest latency setting for this stream, so we'll see how that works out. And let's see, I was gonna make this a poll, but I don't want to deal with the problem of adding freaking, Greek characters to this poll. So maybe I'll just do, A, B, C, or D. But yeah, just as a bit of review, when we have a one sample t-test, when would we do a one sample t-test? Our options are A, when we have the population mean but not the population standard deviation. B, when we have the population standard deviation but not the population mean. C, when we have the sample mean but not the population mean. And finally, D, when we have the population mean but not the sample mean. Let's see how much you have retained from last Wednesday. See how much has stuck in your head over the past week. Ooh, we've got an A. Let's see. Give it a little more time in case anyone else wants to get a guess in there. I think though. And it's okay if you don't remember. Like, that's okay. This is just, checking in. Ooh, all right. That's 2/3 of the current concurrent viewers, so I'm gonna end that poll. I think that's fine. Oh, no wait, all three people have voted now. 3 people have voted. Okay. I'm not gonna turn the poll off. I'm gonna write down the formula for the one sample t and see what happens to those results. The formula for the one sample t-test is the sample mean minus the population mean over the estimated standard error. So let's see, what do we think now? Anyone changing their votes? Are we sticking with it? We're committed now. We're sticking with it. I'm gonna end the poll. The time. I don't think you can change a vote. Oh, that's so weird. Oh, well, then you're locked in. That's so odd though, because I keep seeing these things where like the votes do change. Like I'll have 2 votes and then I'll go back to 1 vote and then I'll have 2 votes. So I always assumed it was people changing votes, but maybe it's just the software being glitchy. Yeah, okay. I have no idea. Either way, A is the correct answer. It can't be B, because we don't have the population standard deviation. That's why we have to use the estimated standard error. So it can't be B. It can't be C, because we have both the sample mean and the population mean. And it can't be D, because, again, we have both of those things. The answer is A. We do a one sample t-test when we have the population mean, but not the population standard deviation. Yeah. I'm gonna do more research into YouTube polls. I'm so curious about like what I'm seeing on my end and why I'm seeing it the way that I do. Either way. So, you are correct. A is the correct answer to this one. Good job. All right. So previously, last time, we talked about the independent samples t-test. That was when you were comparing one sample mean. Oh, no, I want my glasses back. There we go. That was when you were comparing one sample mean to another sample mean. In this case, you had 0 population information whatsoever. Oh, and hi, Hairday. Sorry, I forgot to greet you. Hello, Hairday. It's nice to have you here. Yeah, so you're comparing one sample mean to another sample mean. You have 0 population information whatsoever. And we talked about how we dealt with not having the population standard deviation. That was one of the things that we talked about in the past 2 lectures. And the way that we did that is kind of how we just touched on when we talked about the one sample t-test. We estimated it using this formula for the sample standard deviation. We may not have the full population, but we at least have a little chunk of the population, so we can at least make an estimate based on our sample. Then we use that estimated standard deviation to estimate the standard error. So we just changed the formula to say we don't have the population standard deviation, so we're substituting our estimate, so we get the estimated standard error. There we go. So that's how we coped with not having the estimated with not having the population standard deviation. We also learned about the t-distribution. So for a long time we'd been using z-distributions, but z-distributions only really work when you have population data, like you have the entire population in your data set, but we don't have that anymore. We're working with samples. So the t-distribution is what happens when you're working with samples. We know that smaller sample sizes are probably less accurate to the population and bigger sample sizes are more accurate to the population. So what we did, or well, I didn't do this and we didn't do this, somebody a long time ago, I think William Seeley Gossett, if I remember correctly, did this. What he did was he created this concept called the t-distribution, which is a distribution where your cutoff for rejecting the null changes depending on your sample size. The bigger your sample size, the closer you get to essentially doing a z-test, your cutoff gets smaller. But the smaller your sample size, the less accurate your results probably are to the population, the higher your standards get, the bigger your cutoff becomes. And so we can no longer assume that an alpha of 0.05 was z of plus or minus 1.96. We had to go to that table and look up our critical value rather than just assuming the critical value from z-test would work. And then we also learned this formula, the single sample t-test formula and the independent samples t-test formula. These are the 2 t-tests that we have learned so far. So today, I can already tell the animations I set up on the next slide aren't working, but we're going to deal with it. Today's goal, we want to look at differences within the same sample at 2 time points or in 2 different situations. It's the same individuals that we're comparing to themselves, whether that's before and after, or maybe it's just how do they feel about this thing versus that thing, but we're comparing individuals to themselves. So like, let's say we might be comparing your impression of Madoka Magica before episode 3 and then after episode 3. That would be a repeated measures design. I'm measuring you twice. I'm comparing you to yourself. Maybe in this case, like your current self to your past self. But there are other ways you can do it as well. So, the example that we're using for this. Does watching a scary movie increase anxiety? This is the example we're looking at. So are people more anxious after watching a scary movie than before? And I keep noticing little mistakes on these slides, and this time I'm gonna fix it. I'm gonna fix it. We're doing it live. We're doing it live, everyone. There. Now nobody needs to know except people who download the slides. Or look at the slides. So yeah, I want to know if watching a scary movie increases anxiety. And let's say I measure baseline anxiety levels, so like how anxious are you in general? For 4 people, the week before they see this thriller anime movie, Perfect Blue. Is it Perfect Blue? Now I'm doubting myself. It is Perfect Blue. Good, I got the right title. And what I mean by baseline anxiety levels is how anxious are you in general? Because some people are like very chill. They are not anxious really at all. And then other people like me, we're anxious like all the time regardless of what's going on. People have different baseline levels of anxiety. So I want to know how anxious are these people on just a normal day? Then we measure their anxiety levels immediately after watching the movie. So this is all allowing us to compare how anxious are you normally to how anxious you are right after watching this movie. That's the goal of this one. This is a repeated measures design. I'm measuring everybody repeatedly, twice in this case. Once again, like the previous t-test, we do not know the population mean or the population standard deviation, so we do not have that information anywhere, unfortunately. But that's okay. We can just do what we did for the other ones and start estimating things. So to do this, we need some information. The first thing that we need to do is see how much people changed. And we do this with something called the mean difference. For this, first we calculate everybody's difference scores. How much did everybody change? And we do this by taking their anxiety measures or their anxiety levels before watching the movie and then minus after watching the movie. So we're looking at the difference in anxiety levels before and after watching this movie. And then we take the average difference for everybody. So on average, how much did people's anxiety change from before to after watching the movie? And we call this the mean difference. The average change is the mean difference. That's what this MD stands for. XD isn't the smiling, laughing face. This stands for a difference score, and MD isn't like medical doctor, it's mean difference. Now, of course, there's 2 ways we can interpret this. Let's say that we do find some sort of mean difference. There is some mean difference that is different from 0. So people's anxieties were different before and after they watched this movie. There's 2 possible explanations for this. If the null is true, that means the movie did not change people's anxiety, and the fact that the mean difference was not 0 is probably just sampling error. The true difference in anxiety, the true change in anxiety before and after watching the movie is nothing. The other possibility, of course, is that the movie did affect anxiety, that the mean difference score is meaningfully different from 0, that there was some change in anxiety levels from before watching the movie to after watching the movie. Of course, this raises the usual question with statistical tests. How big of a change is a meaningful change? How big does that average change have to be before we can reject the null and conclude that watching the movie did affect people's anxiety? And to do this, we have to do the usual thing. We've got to create a comparison distribution that represents all of the possible differences that we might have observed if the null was true. So all of the possible shifts in anxiety that we might have seen if the movie did nothing. Because, there's sampling error, right? Like, just people's anxiety reporting might change between those 2 time points for reasons completely unrelated to the movie. Maybe it's just noise, maybe we don't know, but it's possible they could have just changed randomly and it's not meaningful. So how big of a difference would be meaningful? And like, here's all the possible differences we might see in a world where there was no change in anxiety. That's our comparison distribution. It's a distribution of a distribution of differences, assuming that there's no true difference. Like, what would we expect to see just due to noise alone, due to randomness alone? And we have to take that into account when we're deciding how big the difference has to be to reject the null. Now, of course, we don't know the population mean difference. It could be that there was some change in anxiety before and after watching the movie that was completely unrelated to the movie. We don't know the population difference in anxiety between those two time points in the absence of the movie. Like, in a world where the null is true, in a world where the movie had no impact on anxiety, I don't know how much anxiety would have changed between those two time points. But I can make a guess. The assumption here is kind of along the lines of, well, if there was nothing else between those two time points, like if nothing happened between those two time points, your anxiety should stay roughly the same, right? So if your comparison distribution represents everybody who did not see the scary movie, how much should their anxiety have changed before and after? So like, say, the week before to the week after, if nothing special happened. Zero, exactly, Harry. Good job, zero. If nothing happened in between those two time points, theoretically their anxiety should be exactly the same. So we can estimate that in a world where the null is true, in a world where the movie had zero impact on people's anxiety, there should be zero change in their anxiety, right? That's our theoretical population difference. If the movie has no impact on anxiety, there should be no change in anxiety. But of course, we know that the difference score in our sample probably won't be exactly zero because of sampling error. So we need some more information. For example, we do not know how much fluctuation we should see around that zero. Like, there might be slight differences, there might be a slight change in anxiety that's not actually meaningful, that's just noise. And we need to figure out how much of a slight change would we expect just to see due to random chance. And to do that, we need to figure out the standard deviation of our different scores in a world where the null is true, in a world where anxiety didn't actually truthfully change. But we don't have that. We do not have the population standard deviation of the different scores. But we can estimate it. The technique here is going to be the same technique as the one sample t-test. We are going to use our sample standard deviation to estimate the population standard deviation. There's just one small difference. With the one sample t-test, we were looking at the standard deviation of a set of scores, just like raw numbers. In this case, we're looking at the standard deviation of a set of difference scores, so pre minus post. So we're calculating it the same way, just in this time we're looking at the difference between two numbers as opposed to just plain numbers. And I promise I'll like give concrete examples because I think that's a little abstract right now, you know? So here are our 6 steps of hypothesis testing, and I'm going to highlight the ones that have changed a little bit from last time in red. The first, your null and research hypothesis is still the same. Your null hypothesis is that there is no difference. Your alternative or research hypothesis is still there is a difference. So this is exactly the same as it has been for all of the t-tests and the z-score and z-test that we talked about. This has not changed one bit. There is a difference or there is no difference. The second step, however, has changed a bit. For the comparison distribution, now we're not talking about a distribution of scores like we were with the one sample t-test, and we're not talking about a distribution of differences between two means like we were with the independent samples t-test. This time we're talking about a distribution of mean differences, which is a little hard to wrap your head around, but it's a distribution of the average change, I guess you could say, or the average difference between two numbers. That's what we're comparing our sample mean to, that average change of 0 if the null is true. Step 3 is still the same. We still use our degrees of freedom to look up our t-critical value in the table and use that as our cutoff, so that hasn't changed at all. Step 4, however, we're using a different formula now. For the one sample t-test, we use the one sample t-test formula. For the independent measures t-test, we use the independent measures t-test formula. And now we have our repeated measures, or our paired or our dependent means t-test formula. Whatever you want to call it, it's the same freaking formula, so I guess the name doesn't really matter in that respect. But yeah, we're just using a slightly different formula. And you make a decision exactly the same way. You compare the t-test, or the t-value that you got from your t-test, to the critical value from step 3. You compare what you found to your cutoff, and then decide whether you can reject or fail to reject the null. Then finally, you interpret your results the same way. If you reject the null, you say there was a difference. You fail to reject the null, you say there wasn't a difference. So here's our example. Again, just to remind you, our example was that we want to know whether watching scary movies increases anxiety. So I measure 4 people, their baseline anxiety levels, how anxious are they on just a random day, a week before they see the psychological thriller anime movie Perfect Blue. Then, immediately after they finish watching the movie, I measure their anxiety levels again, and my goal is to see, did their anxiety levels go up or maybe even go down after the movie? So here we go. Let's state our hypotheses. Our null hypothesis, of course, is the usual. There's nothing going on here. There will be 0 difference in self-reported anxiety before and after watching the movie. Any, tiny numerical difference that we might see isn't actually meaningful. It's entirely sampling error. Of course, the alternative or research hypothesis is that there is a difference. There is some kind of difference. There will be a difference in self-reported anxiety of people after watching the movie versus before watching the movie. So, same as usual. So that's step 1. Step 2, we calculate our comparison distribution, or state what is known about our comparison distribution. Now, we already talked about this. The comparison distribution represents a world where the null is true, where watching the movie had 0 impact on anxiety. So that means the mean difference of this distribution should be 0. If the scary movie had no impact on anxiety, then the change between before and after watching the movie should be 0 change. Anxiety levels should stay the same. Next, we have to figure out our degrees of freedom, and this is going to be a little weird. I know some of my students have had trouble with this in the past. We had 1, 2, 3, 4 participants. But the weird thing here is that we have 8 measurements, right? We have a measurement from each of the 4 before, and then a measurement from each of the 4 after. The repeated measures, or dependent means, or paired, or whatever you call it, this t-test does not actually count these scores. It doesn't really count them. The only thing it cares about is the difference score. It cares about the difference between before and after. It's not actually doing the t-test on these 2 sets of scores. It's doing the t-test just on the difference scores. So in this case, our sample size is 4. We've got 4 people, so n is 4. And we're going to have 4 different scores, 1 for each person. So our sample size is 4, but the degrees of freedom formula is still the same. It's your sample size minus 1. We had 4 people, a minus 1. Our degrees of freedom is 3. That trips a lot of people up. I know it's very tempting to treat this like an independent measures t-test with the degrees of freedom, but no, it's not like that. It's not like an independent measures t-test. It doesn't count as 8 observations, it only counts as 4 observations. Because we're working with the different scores, not the scores. Your next step is to get the sum of squares of the different scores. So here's our nice table. We've got person 1, their anxiety before the movie was 0, their anxiety after was 3. Person 2, anxiety was 0 and then 2. Person 3, their anxiety was 2 and then 5. And person 4, their anxiety was 0 and then 1. The first thing that we've got to do before we can do anything else is we have to calculate, here's the formula, the sum of squares of the different scores, which means we need the different scores. We've got to figure out the different scores. So let's do some math. The different scores are pre minus post. So in this case, 0 minus 3, the difference score for person 1 is negative 3. Based on that, what is the difference score for person 2, or participant B? What is their difference score? I know, I'm talking to you for the first time in a minute. Negative 2. Good job, Herde. Indeed. 0 minus 2, negative 2. How about person C's difference score? 2 minus 5. But it feels weird to use initial minus final. I know, it does feel weird, doesn't it? Yeah, -3. It does feel weird, doesn't it? Because it's like, the weird thing about this is that the scores are going up, but the differences are negative, which is very counterintuitive, isn't it? A lot of the time, people will actually not report positives or negatives. I got you at the worst moment, didn't I? That's my sneaky, sneaky technique, is somehow I know when the worst moment to ask the question is, and I get you. All right, and then the last one is 0 minus 1, so -1. There we go. Now our goal is to find the mean difference score. To do this, we add up all of our difference scores and divide by the number of difference scores. So that is -3 plus -2 plus -3 plus -1, which I hate adding negative numbers. It's like what, -5, -8, -9? Is that -9? I think that's -9 divided by 4. Thank you. Thank you, Astrologopers, for helping reassure me that my math wasn't totally... So that's 2.25. The average difference score, the average change is -2.25. You know, it's adding numbers normally than adding a negative at the end. That's true. That is true. There's just something about it that trips me up. I think it's because I'm always worried there's going to be positives in there with the negative, and once that starts happening, my brain starts starting to mush. Oh, it's sad. It's not that bad. You are so right that that's the case, but I don't know. Negative numbers intimidate me. All right. Now, what we have to do is we have to take each number, subtract the mean, so each difference score, subtract the mean difference score, and then square that, which is already making me want to cry. I will not lie to you. Fair signs are perpetually a problem, especially I and its trippy issue. I don't even want to think about I. I'm gonna be honest. I have not thought about I in years, and I have been happier for it. Forever thinking of that time Phi called me and Z the math people in V theorem. No, that's just Z. I'm just here. I'm doing stats, but I'm scared of math. You put that I near me and I will run away. Math V2, hello Phi. Perfect timing. Square root of I is the problem. That also scares me. Y'all are making me want to run away. This is like reminding me of like, you know, like holding a cross out in front of a vampire. Hi, just dropped in, math person in V theorem. Can you help me with imaginary numbers? Hi, Xeno time. Anyway, I will be heading out now. I'm kidding. We gotta finish the lecture. But oh my gosh. My fight or flight. Speaking of increasing anxiety, it's happening. Okay. So, we've done sum of squares before. Do you mind if I just like skip through the whole like... Well, let's do it for at least one. I'm gonna be a good person. I'm gonna do it for at least participant A. We have -3. So that's their difference score. Subtract the mean difference. So -3 minus -2.25. I hate it. -3 minus -2.25 is essentially -3 plus 2.25, I believe. So -0.75. Yes, thank you. Thank you, Astrologopos. -0.75. So that's gonna be -0.75, and then we've got to square that, which is gonna be about 0.56. 0.56. It's all so gross. And then we do that for all of the other ones as well. And frankly, I do not have the courage to do that for every single one of them. But essentially, it's each number minus the mean difference and then square that deviance score. It's the same as the sum of squares that we've been doing this whole time. Then once you have all the different scores, you add them all up to get the sum of squares of the different scores. Which I think I should have some sort of animation here for that. There's going to be our nice formula. Okay, there you go. There's your difference scores. There's your mean difference. I'm always happy to see confirmed in my slides all the math that we did, though that was really just me like flailing in the dark, and then Heraday and Astral just confirming things making sure that I did things right. Thank you for your service. And then we get all those deviance scores, so how far those difference scores were from the mean difference, and then we square all of those, add up all the squared deviance scores. Our sum of squares is 2.75. The formula for the standard deviation of the difference scores is still the sum of squares over the square root of the sum of squares over the degrees of freedom, which is the formula that we have been using all this time. Just in this case, it's the sum of squares of the difference scores as opposed to like the sum of squares of of the two groups, or the sum of squares of the raw scores. Like whatever it is, it's still the same deal, So the sum of squares of the different scores divided by the degrees of freedom. In this case, the sum of squares of the different scores that we just calculated was 2.75. So that's going to be the square root of 2.75 divided by the degrees of freedom. We had 4 different scores, minus 1, 3. This is too much math for me on a work night. Okay, so that's 2.75 divided by 3 is, did I punch that in right? 0.92, I think. So that's going to be the square root of 0.92. Then we take the square root of 0.92. Our standard deviation of the difference scores will be about 0.96, roughly. There we go. So our average difference score was negative 2.25, and we can expect that, and on average, the difference scores were about 0.96 away from that negative 2.25. Next, we can use that to calculate our standard error. And again, the formula for the standard error is the same as it has been. It's the standard deviation over the square root of the sample size. The only thing that's changed is the standard deviation of difference scores, as opposed to the standard deviation of just scores or whatever that we were using before. Nothing really's changed. So the standard deviation we just calculated was 0.96. Divided by the square root of our sample size. Again, we have 4 participants and 4 different scores, so our sample size is 4. So that's divided by the square root of 4. 0.96 divided by the square root of 4. What's the square root of 4? What is it? Tell me your secrets. 2, correct. So I really like having my students do that kind of thing. Or negative 2. I don't think there's any i's in here. I think it's just 2. Yeah, 2. Right, so and now we have to do the 0.96 divided by 2. 0.96 divided by 2, that's what? 0.48, I think? 0.48. Negative 2 times negative 2 equals positive 4. You're right. Astrologicals, I'm gonna fight you. I'm not gonna actually fight you. But you're doing math brain things to me. And my brain is... Rather than think too hard about that, my brain is getting ready to return to Moth. I'm gonna go fly into a light bulb. But no, we have a lecture to finish. We're gonna do it. Okay. All right. So we have our standard deviation and we have our standard error. Oh, and I have this all animated out so you don't have to deal with my handwriting. Look at that. Look how beautiful. It looks like I rounded to more decimals here, so the answers that we get here are probably going to be slightly different than the ones that we calculated, but don't go into the light yet. When am I allowed to go into the light? Goals. Next model will have a toggle where I straight up turn into a moth. I'm going to be reverse Juniper. Or maybe that's just Juniper, I don't know. Oh, I think that's just Juniper at that point. Anyway, return to Moth. I must leave. I must go back to my people. Anyway, so that's step 2. We've established our comparison distribution. The mean of our comparison distribution, a world where Scary movies that have no impact on anxiety would see 0 change in anxiety. And our standard deviation is 0.957, and our standard error is 0.479. I should have a crazy anime transformation sequence. That would be an interesting thing to do to practice animation. That would be fun. Huh. I don't know if I'm quite at that level yet, but it would be fun to make like a transformation sequence. Just like one of those elaborate magical girl transformations, and there's a big poof of smoke, and it's just moth. That could be fun. Anyway, okay, so that's step 2. Step 3, we've got to set our cutoff. So we have our degrees of freedom, 3. Which means that we're using our usual t-table, and because our degrees of freedom are 3, we're going to the row labeled 3. As per usual in psychology, we're doing a two-tailed test with an alpha of 0.05. So we go to proportion and two tails combined, alpha of 0.05, this column. Here it is zoomed in so you can actually freaking see it. And we go where those two things meet, the degrees of freedom of 3 and then 0.05 and two tails combined. Our cutoff is plus or minus 3.182. That's the number that we've got to beat. That's the t-value that we have to beat to reject the null. And for some reason I have this slide again, except this time it actually tells you the cutoff. All right, so that's step 3. What do you do if there are negative degrees of freedom? It's below freezing and snowing where I am. Luckily, degrees of freedom never go negative. If your degrees of freedom go negative, that's an indication that something has gone horribly wrong, because your degrees of freedom is the number of people you have in your study minus 1. So either, if your degrees of freedom are negative, you either didn't have a single person in your study, which is a problem, or you had negative people in your study, and I don't actually want to know what that would mean. That's a little scary. The weather app says negative 10 degrees of freedom, I think. I don't even want to look at my weather app. I know it's going to be negative, so I'm just not gonna. It is an interesting thought, though. The cryptid lover in me is like, what is a negative person? What would a negative person or a negative observation be? I want to know. I want to know. Fahrenheit would be degrees of freedom because America. Oh no, it's America, oh no. Oh, okay, anyway. Step 4. Let's do our t-test. Gaster undertale negative person. Is that how it works? Gotta go to the TV tropes page for unperson, I believe. Antimatter person completely identical but explodes when touching anything. Oh no! Or like, if we think of the degrees of freedom as the number of observations that you have minus 1, then negative observations could just be somebody went into your data and started deleting things from your data set and corrupted the file, maybe. I don't know. I'm overthinking this, but it's a fun thought problem. Maybe this isn't the place to think about it, but this is exactly the kind of thing where I would like to take the bit way too far and just overthink it so much. But I'm not gonna do that. I gotta get up early tomorrow, so I can't afford to go that far on a shenanigan tangent right now. All right, so let's run our t-test. The mean difference that we calculated was negative 2.25. So that was the average amount of change, minus the hypothesized difference if the null is true, which was 0. Will the discovered anti-elements be in the tier list? Xenotime, are you making a tier list of elements or something? I'll watch that. Okay, right. So this part of the equation is always going to be 0. Like, you're comparing what you found to the null hypothesis 0, so this part of the equation will not actually really affect your math at all. You can kind of ignore it, more or less. It's just there to say, this represents the null hypothesis. And then we divide by the standard error of the different scores. I forgot to mention this before, but this is the symbol for standard error for different scores, and it is hellish to type, because it is S subscript M, and then subscript on the subscript D. So S of M is the usual way of writing the standard error, but they had to put a D there because it's the standard error of different scores, and that is just a gigantic headache and should never happen. All right, anyway, So our average difference score was negative 2.25, divided by our standard error, which is 0.479, give or take, based on rounding. And we end up with a t-value of negative 4.7. Oh yeah, you're doing an elements stream tier list stream tomorrow. I want to see it. Double subscript, my handwriting already makes one subscript hard to see. I want to see you try and write the standard error of the mean differences. I would love to see that. Me trying to write it during class is like, luckily I know that I have to start out big to write it, but it's just downhill. Usually I like to put one thing in superscript and one in subscript if there's two. Oh yeah, so like you could put the S in superscript, the M in normal, and then the D in subscript. But that would look weird because then the M would be so much bigger than the other two. I'm not going to think about it too much. I've never seen a standard error of mean differences reported in a psychology paper. Therefore, I'm just not going to think about it too much. Or actually, if it is reported in a psychology paper, usually standard error is just written as SE. So, like, it doesn't matter. You're probably not going to be typing up SMD unless you are creating, like, slides or something for a stats class. I sometimes put subscripts and superscripts because, I don't know, I'm bad at writing. Yeah, that's fair. Yeah, oh my gosh, it's pain to look at. I can't. Anyway, we have our t-value. Let's go on to step 5. Decide whether we can reject or fail to reject the null. So here's our distribution. We looked up our critical value. Our critical value was plus or minus 3.182. If the t-value we calculated is beyond that, it's in the tails, it's farther from 0 than our cutoff, we can reject the null. If the t-value is closer to 0 than that, in the body of the distribution, we fail to reject the null. The t-value we calculated was about 4.7, give or take, rounding, you know. So do we reject or do we fail to reject the null? Reject, correct. We reject the null. Our t-value met our standards. It was beyond our cutoff. It was out in the tails. It would be very unlikely that we got a sample with a mean difference that far away or that big if the null was true. Is it still possible? Yes, but it would be very unlikely that this was just a fluke. Yesterday I was doing CS math and represented the junk state as S superscript J. At that point, given I got really sick on an SJ train. Walked. I feel like 90% of that sentence just went over my head, other than you were sick and on the train and therefore you were not going as hard as you could have, which is completely understandable. I endorse taking it easy and cutting corners if you're completely burnt out and tired. As long as it works, you know? Doesn't have to be the perfect solution every time, as long as it works and you're not going to hurt anyone with it. And I doubt, like, writing it that way is going to hurt anyone, right? You know, so it's probably fine. All right. So, effect size. We've determined that we have rejecting the null, but let's figure out how big of an impact this was. SJ is junk, their train made me sick. You know, I've gotten used to motion sickness, but I get that. I get that. I have definitely gotten sick on the train before. And I will again. I have faith in future me to get motion sick again. That's why I don't play many video games on this channel, because I get motion sick playing video games very quickly, which is deeply unfortunate. I've been playing Minecraft with some of the other V-Theorem members, and I can only be on the server for like an hour at a time before I get so motion sick I need to go lie down, which is super unfortunate because I love Minecraft and I can play for hours on console. But everybody else in V-Theorem plays it on PC, everybody who plays it, so if I want to play with them, I just gotta play for an hour at a time max because the motion sickness gets me. Maybe it's for the best. I don't know. Anyway. Yeah, I get really sick in cars, trains, and planes are usually chill as long as you're not backwards. Yeah, I would agree with that. I have this problem where, like, I used to try and draw when I was in the car or on a bus or in a train, and that is, I think, the single worst thing you can do for motion sickness, at least in my experience, is drawing there. There's probably controller support or at least a mod that does it. Yeah, there is. I have found a mod that allows me to play it with controller, and that does help a little bit. It doesn't help a whole lot, but it helps a little bit. I haven't implemented that when playing it with the other V-Theorem people yet, though, because it's kind of a pain to set up. I've got to map the controller and everything. But maybe I should do that if we end up playing it more. 30 degrees tilt. Oh my gosh. Oh, even the trains near me aren't that bad. It's pretty rough. Okay, effect size. Let's do this. Effect size. Oh my gosh. So the effect size for the repeated measures t-test, Cohen's d specifically, is the same as it was for the one sample t-test. I just changed the notation, or not me, but we've changed the notation a little bit to like say these are different scores, but mathematically it's the same. You take your mean difference, so the average difference between before and after, minus the hypothesized, so this is just 0, it doesn't affect anything, divided by the standard deviation of the difference scores. So we calculated the mean difference as negative 2.25. Of course, the hypothesized mean difference if the null is true is 0. So again, this doesn't really actually affect the formula. You can leave it out. Divided by the standard deviation of the difference scores that we calculated way back in step 3, which was about 0.957, give or take with rounding. Which ends up being, and I know this because I have spoilers on the preview for the next slide, is negative 2.35. That's the Cohen's d for this effect, is negative 2.35, which would be considered a pretty big effect. Like in psychology, this would actually be really a huge effect. This would be, yeah. I know that like Phi probably wouldn't be impressed with this effect size, but as a psychologist, I would be. There are other ways to measure effect size, if you remember correctly. Yes, you would absolutely be right. We could also do R squared here. I have memorized the formula for R squared for a t-test as well. Any t-test, R squared is always the same. It is the t-value you calculated squared over the degrees of freedom, or, well, I guess the order doesn't matter here, but just in case. The t-value you calculated squared plus the degrees of freedom. That would be another way that we could calculate or quantify effect size for this. Oh, I'm hiding. I'm going down and becoming shorter. Yeah, there are other effect sizes, and like these are the main ones I know how to calculate for t-tests, but there are a lot of other different effect sizes, like there's F, there's omega squared, there's eta squared, there's generalized eta squared and partial eta squared, there's a bunch of different effect sizes. I don't even know all of the effect sizes. There's standardized betas, there's odds ratios, which are kind of both a test statistic and an effect size. Like, yeah, there's a lot of different effect sizes. These are the two ones that I've talked about so far in this class, but there are way more than that out there. All right, so that's step 5. We determined to, oh wait, I want to read this. There are like 25 people per kilometer in Sweden. Why are they turning that sharply? Surely there's room for a smoother turn. Longer tracks cost more money is all I'm saying. Or maybe they just got a theme park designer to design their railway. I don't know. I mean, are some effect sizes not defined for some tests? Yeah, there are some cases where it's not possible to calculate certain effect sizes for certain types of tests. For example, chi-square. I forget the effect size for chi-square. I forget what it's called. But chi-square, because there's not variability, it isn't based on a normal distribution. It's not called, it's not a parametric test. Chi-square does not have things like the standard deviation or anything like that, so you could not calculate, say, Cohen's d or R squared for a chi-square. I wonder if there's a way to calculate R squared, but you definitely couldn't get Cohen's d for a chi-square. you could calculate the chi-square effect size and then convert that into another effect size and maybe eventually convert it into Cohen's d. This is a big problem that people have when they're doing meta-analyses, where they try and combine the effects of a whole bunch of different studies to see, like, across these 100 studies or something, does this work? But to do that, to do a meta-analysis, you have to convert all these effects from all these different studies that were using all kinds of different measurements and statistical tests and stuff, and convert them all into the same type of effect size. So there are ways to convert between effect sizes, but there may not be a way to directly calculate an effect size for like any given statistical test. So like if I wanted to do a Cohen's d for a chi-square, I could not calculate that correctly. Maybe I could like convert the chi-square effect size into like r squared and then convert r squared into Cohen's d or something like that. But yeah, it's not always possible to directly get an effect size. And then especially some of the newer statistics that exist out there, it's just straight up impossible. There is no effect size invented for them yet. So you couldn't even calculate an effect size to convert for those ones yet. They're just, nobody's invented a way to do it. Yeah. I mean, the basics of statistics are fairly static. Like the stuff that I'm teaching hasn't changed a lot in many, many, many years now. But like the cutting edge of statistics is moving pretty quickly, I would say. Like, I mean, well, of course it is. AI is based on statistics. But yeah, like this stuff stays pretty constant, but there's a lot of newer stuff out there where like, yeah, maybe there just straight up isn't effect size out there yet. Or something like that. Yeah, sorry, I just rambled on. I think it's an interesting problem. This actually came up. I do some like meta science, like science of how people do science and like evaluating methods and statistics in science, or at least I used to back in the day. And one of the problems that we came into, there was this thing where we were trying to, a lot of people were saying psychologists should always report effect sizes. They should always report effect sizes. And what we did was, yeah, they do. Yeah, there's a lot of really new, cool statistics out there that I haven't learned much about, but there's not a lot of innovation when it comes to like t-tests and ANOVAs, but that's largely because, at least in psychology, t-tests and ANOVAs have really fallen out of fashion. Like you're not seeing these all that often as like the primary hypothesis test in a given paper. These days we're almost exclusively in the land of regression, and regression's growing a lot. Yeah. The t-test, I think, is actually pretty, because William Seeley Gossett came up with the t-test, and he came up with the t-test in, it was called Student's t-test at first. That's a whole story. Seeley Gossett came up with the t-test. When did he come up with it? He was working for Guinness, though, you know, like the beer company. And he came up with the t-test. It looks like in the early 1900s. So this is actually pretty early. The t-distribution was in the late 1800s, but it looks like it kind of really got its start when he published his paper in the early 1900s. Yeah, it was a whole thing though, because like he was working for Guinness and the beer company, and he needed to come up with a way to compare using samples without any population data. And so he came up with the t-test using that concept of the t-distribution. But Guinness wouldn't let him publish it because, you know, they're a company and they want, you know, like to make money and stuff like that. Or like he knew they wouldn't let him publish it and give it out in the open. So he worked with a journal editor. I think the journal was Biometrica or something like that. Yeah, and he published in the journal anonymously under the name Student. Oh yeah, Biometrica. He published it in Biometrica under the name Student, and eventually we found out that it was him who did it. But like, he was anonymous for a long time because he was afraid the company would get mad at him for releasing company secrets because he came up with this for the company, you know. But yeah, it feels like pretty recent history, you know, like the early 1900s. The t-test is only a little over 100 years old, which in the grand scheme of things feels really, really recent, you know? And the t-test was like invented to deal with the problem of dealing with samples. So I imagine like a lot of other things, like I haven't looked into this, but like ANOVA probably is more recent than that. I should look into this sometime. I should look into like I'm always scared to look into the history of statistics though, because like a lot of people who created statistics were using it for interesting reasons. Yeah, right? It's like, yeah, so statistics is changing a lot. But yeah, we're kind of past the time of t-tests and stuff for a lot of things. Yeah. Anyway. Mhm. Okay, right. Let's go on to step 6. We've been dawdling enough. Yeah. I'm just glad that I can tell the story of William Seeley Gossett without being like, he invented this for eugenics or something like that, because. Anyway, let's interpret our results. So, if you remember, the study that we were doing here was looking to see if people were more anxious after watching this scary thriller movie than before watching it. And that's what we found. We rejected the null, so our sentence write-up might be something along the lines of people were more anxious after watching Perfect Blue compared to before watching Perfect Blue. So we know that there is a difference, so I can say there was a difference in anxiety between before and after. And if I want to know what that difference was, I just look, was the mean of anxiety higher before or after? Then, of course, we have our usual APA style statistics. T, because we did a t-test using the t-distribution on 3 degrees of freedom. So now if they want to look up our critical value, they can go to the t-table in the 3rd row. We calculated a t-value of negative 4.7. We rejected the null. P is less than 0.05. And then our effect size Cohen's d is negative 2.35. Now, if you're like reading a scientific paper or something like that that uses a t-test, a lot of people will not bother telling you whether the t and d values are positive or negative. They just won't bother because you can't really get much meaning from that. Like, especially for independent t-tests, there's no reason you had to put one mean first and the other mean second, and that's what determines whether it's positive or negative. So that's kind of a lot of people just straight up don't report whether their t-value is negative or not, because it's not really giving you much useful information a lot of the time. You could argue that it's more likely to give you useful information in repeated measures or dependent, whatever you want to call them, t-tests, because usually it's before minus after, and that way a negative t-value might indicate numbers went up and a positive t-value might indicate numbers went down, but a lot of people just don't report the negative for a t-value. This would be solved by an absolute value in the equation. I have so many feelings that we should be using absolute values a lot more in statistics. Yeah, that's what I have to say on that matter. I guess. I have feelings about that, but apparently some people don't. I was wondering why we square numbers in the sum of squares instead of just using the absolute value to make everything positive. And apparently there is a method of calculating some sort of standard deviation using absolute value instead of squaring the numbers. But for some reason it gives you a slightly different result, and I'm not mathy enough to fully understand it. And the absolute value, apparently they settled on the squaring because they thought it was like a better, cleaner way of doing it. But if you're working with sample data, apparently actually the absolute value works a bit better. But we've been using the standard deviation method with the squaring for so long, that's just kind of become a habit. So maybe we will see a change in like these basic types of statistics coming up in the next few years, where we switch from using squaring to make things positive to using the absolute value. I don't know. I would advocate for that. I think the absolute value makes a lot more sense than just squaring stuff. But what if some of your values are complex? I don't even know what that means, and I'm living in blissful ignorance about that. Is it the thing where people just do the absolute value implicitly? That seems to be what's happening with the t-test anyway. Like, at least as far as reporting is concerned. Just straight up people not report t-values as negative. Yeah, what about imaginary numbers? I don't play with imaginary numbers. You know what? Imaginary numbers, I'm kidding, I'm not going away. It was a little scary though. a little scary. I'm just a small moth. I'm just a small moth. I am not brave enough to face the imaginary numbers. I'm gonna put on my blankie. Imagine numbers couldn't be me. I'm putting on my blankie to it will protect me from the complex and imaginary numbers. Oh gosh. My blankie can't save me now. Help! Help! Okay, we're gonna keep going. We're gonna keep going. If I keep going, then I don't need to think about the imaginary numbers. Can't catch me. Can't catch me. I'm going too fast. I'm going too fast. Okay. Come on. Go. All right, so, one of the interesting things, so here's the table of numbers that we calculated earlier when we were figuring out the standard deviation and the standard error. One of the interesting things about these repeated measures designs, these within subjects designs where you're measuring the same people twice, our standard deviation of the different scores was this. But if, say, I took the standard deviation of the raw scores, the original scores, it would be much higher. Not for the, this is a bad example, but here. Generally speaking, raw scores, so if I just took the raw anxiety scores before I did any math to them, generally speaking, that standard deviation, that variability would be considerably higher than the variability of the different scores. This is a fancy property of different scores. Different scores, so before minus after or whatever, tends to have lower variability than just ordinary scores. Which is one of the main advantages of these repeated measures designs. Repeated measures designs have more statistical power than other designs, than between subjects designs. Because they have less variability. They're dealing with different scores, which means they have less variability. Variability is what we use to estimate sampling error. You can see, if you look at the formula for the t-value, a bigger t-value makes it easier to reject the null, right? Your sampling error is on the bottom. The smaller your standard error, the smaller your variability is, generally speaking, the bigger your t-value. So you would like to have smaller variability and less sampling error. Because different scores have less variability, mathematically speaking, it will give you less sampling error, which makes it easier to get a big t-value. The sort of higher level way of thinking about this is that I am eliminating error due to individual differences. I mentioned this earlier, but some people are just never anxious whatsoever. They're always calm. And other people, like me, are consistently anxious. In a between subjects design, I only see you at one time point. I don't know if you're very anxious now because of the movie or if you're just always very anxious. I don't know if this person's not very anxious because the movie didn't affect them, or if they're just a very calm and hard to shake person, I don't know. I cannot account for that. But with a repeated measures design, I have you before and after. I can see if your scores were high both before and after, you're probably just a high anxiety person in general, and I can factor that out. If your scores are low before and after, you're probably just a generally low anxiety person, and I can factor that out. I couldn't figure that out before. With a between subjects design, I just have to chalk that up to error. But here I can say, no, that's not error. I know where that's coming from. Yeah. Isn't it nice? Oh, thank you. Yeah, I think the math I try, but yeah, I think here the math really cleanly connects to like the higher level practice here, because I don't know, it feels so clear to me at least. But yeah, basically different scores account for this person's always higher, this person's always low. So they have smaller variability, which means you have less sampling error, which leads to bigger t-values. So it's more powerful. It is easier to find a significant effect. It's easier to reject the null with one of these repeated measures designs than with a between subjects design. That's what more powerful means, just as a review. More statistically powerful tests they make it easier to reject the null, assuming that there is a real difference in the population. Like, assuming there's something there, these tests have an easier time finding it. And that's the main advantage of this type of t-test. It can find things that a between subjects design couldn't find. This is nice because it means you don't need as many participants to get an adequate amount of power for a study. I can do this type of t-test, I can do this type of design, and I don't need nearly as big of a sample as I would if I was doing it a between subjects design. It's more powerful than the independent measures t-test. This is great for a lot of reasons. It's more economical. Like, let's say I'm doing fMRIs or something like that, or maybe I'm doing a mouse study, like I know, like the paper I read when I was collabing with Phi was a mouse study, and I have learned from Phi that mice are incredibly expensive to upkeep, so you cannot have a huge sample size in one of these mouse studies. You don't need as big of a sample size if you're using this type of statistic. You don't. It's great. So it's more economical, you can save a lot of money because you don't need as many participants. It's also great for if you're studying a really unusually rare population. Let's say I'm playing gotcha players. If I grab like 100 random people off the street randomly, it's unlikely I'll get very many gotcha players in there. But I don't need to worry about my sample size as much. I don't need as many people. So if I'm studying a really rare group, like people who, I know gotcha players don't feel rare, but like if I'm studying a really rare specific group, like gotcha players or people with a very specific subtype of schizophrenia or people who have experienced a very specific life experience or something like that, a repeated measures design means I don't need to seek out as many people in this rare population. It makes it more doable to do good research with a very small population. It's also a great fit for studies that take place over time, right? Like it's naturally looking at before and after. So it makes a lot of sense to use this kind of design if you're looking for change over time. Of course, there are downsides though. Not everything's great. I mean, the upside is it's more powerful, so it's easier to find things. You don't need as many people. You don't need to spend as much money. And it's a good fit for overtime, but downsides also exist. So one of the first disadvantages has to do with study design. Let's say I am looking whether mindfulness training, which is kind of like meditation, I'm looking at whether mindfulness training makes people happier. So I measure how happy they are before, I give them the training, and then I measure how happy they are after. Now this seems great and all, but there's a problem here, and that problem is that something other than the mindfulness training could happen in between my pre and post measurements. It's entirely possible that something else happened in between. So let's say I'm doing this on like a student population. I measure their baseline happiness, sort of their average happiness, during a time that happens to be their spring break. So they're probably very happy. Then I give them the mindfulness training, and then I measure their post-intervention happiness during midterm exams. Not great, right? If I see any difference between before and after, I don't know if it's due to the mindfulness or just when I took my measurements. And if I'm like doing this in contact with the school, but I'm not paying attention to their academic calendar, I might not even know this is a problem. This is especially a big problem if you're doing like a really long-term study, these longitudinal studies that take place over months or years or even decades. Like big events, big global events can really screw you up. For example, the COVID-19 pandemic screwed up a lot of repeated measures designs because now there's this huge thing that happened in between your before and after measurements that vastly changed everybody's way of life for a pretty significant period of time. Now you don't know if your intervention in between your before and after caused the change or if the pandemic caused the change. You have to either completely change what your study's about or throw out your data entirely. So this is one of the major problems. You cannot... There is a real risk that something other than your manipulation could happen between your time points, and that can affect your results. There's also some other problems with measuring the same people multiple times. Another problem is measuring somebody once can affect the measurement the second time. One version of this is order effect. So order effect is like the order you do the tasks affects how you respond to the tasks. So let's say I have you do an incredibly difficult calculus exam, and then I have you do something else immediately after. You're probably like burnt out, your brain is mush from doing that incredibly difficult exam, and you're going to behave differently on no matter what you do next. regardless of anything that I do in the middle, maybe I give you a chocolate bar or something, your brain is still mush from that cognitively taxing thing you just did. I don't know, I like calculus. That's fair. That's fair, Astrology was. What's something that's very cognitively taxing that you hate? I would say doing your taxes, but I think that's not as much of a problem in countries other than the one that I live in. Cognitively taxing thing that isn't calculus that somebody... Well, this isn't a cognitively taxing thing, but, wait, wouldn't a control group help with this? Yes, a control group would help with that, but at that point, it's no longer a purely within subjects design. You've added the between subjects element, right? Because you have the control group and the treatment group, and people aren't in both, you know? So, yeah, that would, mindless dumb work. Oh, like doing mindless dumb work. Yeah, but then you're still measuring the same people twice, right? And you still might risk this fatigue there. Like, if they have to do a cognitively taxing task, you can't get around that. They're going to have to do it at some point. This can also go for physically taxing. I was once, I wasn't part of this study, but I saw some colleagues doing this study. It involved walking up a very heavy, or a very steep slope in a very hilly area while carrying something very heavy. That was physically tiring. No matter what the participants did after that, they were going to be achy, they were going to be tired, they might be out of breath, you know? Like, the fact that you did that thing first might affect whatever happens next, regardless of whether you want it to or not. There's also pattern recognition. Can you randomize the order and you'll get variance, but not bias? Zeno time, you're on to something. You're on to something. Yes. I'm going to do this next one first, but then I will give you the technical jargony term for exactly what you're describing. Very, very good observation. Yes. So the other problem is potentially, let's say I'm having you solve logic puzzles or something like that. You know, like Z a while back did that Raven's matrices thing. That's just a bunch of like image spatial reasoning puzzles. The more of those you do, the better you get at them. So if I want to measure your reasoning before and after some sort of intervention, you're going to do better the second time because you've had practice with those problems, right? So, like, that's also a problem. You're going to do better the second time no matter what because you've already gotten some practice in there. So the solution that Xenotime pointed out, and this works for sometimes but not always, is called counterbalancing. This is exactly what you were pointing out. Counterbalancing is where if you can just, like, if your study design allows it, if this isn't like a before and after thing, it's just conditions can be in any order and it doesn't matter. Just swap which condition people get first. Some people get the tiring one first, other people get the not so tiring one first, and then any exhaustion effects should wash out. That's the idea. Or like any practice effects should wash out. Practice effects are a little more difficult to do this with. If you're doing the same measurement twice, that's always going to be a problem, which you often have to do for your dependent variable, but depending on what you're doing, maybe you can counterbalance it, or maybe you do a similar set of problems and then you counterbalance which set they get. So like Raven's matrices set A, Raven matrices set B. Some people do set A first, other people do set B first, but yeah, counterbalancing, that's exactly what you were talking about. Just randomize which one the order that they do things in, and that works well as long as the order doesn't matter. Another thing you have to worry about, though, so that's a solution to this problem. And it doesn't always work, but when it works, it's great. But there's another problem. In this case, participants are responding to the same thing twice, because I want to measure if measurement changes over time, right? I want to measure if their anxiety changes over time, so I want to use the same measure of anxiety both times, or the same measure of whatever it is. Ideally, I'd be using the same measurement both times. And people start doing weird stuff when you ask them the same questions twice. There's this thing called demand characteristics. Demand characteristics are where people start acting in a certain way because they think that that's what you want them to do. If I ask you, how happy are you right now on a scale of 1 to 5, and then you say like 3, and then I ask you exactly the same question, there's two possible outcomes related to demand characteristics. One, you might feel like, well, I just said 3, so I better say 3 again. Yeah, exactly. It's exactly that problem of overthinking it if a question has been repeated. So like, well, I just gave the answer 3, so I better give the same answer again, even if your happiness has changed. Alternately, It could be if somebody asks you the same question twice in a row, you might think, oh, they're looking for a different answer this time. So I just answered 3, I better answer something else, even if your happiness level hasn't changed. Oh, I didn't go to the next one. But yeah, that is demand characteristics. People will overthink it, essentially, and they start responding in weird ways. Vsauce taught you about demand characteristics? That's so cool. I did not know that they had done something with that. That's neat. But yeah, this is that thing. Another risk related to this is because this is a repeated measures design, everybody's in every condition, that means your participants see every condition, which makes it easier for them to guess what you're testing. If they see both conditions, they might be able to guess your hypothesis. And people can start doing really weird stuff when they guess your hypothesis too. Some people, when they guess what your hypothesis is, they'll try and give you the answer that you're looking for. They'll say, oh, they think that this is going to make me happier, so I better tell them that I'm happy, even if you're not. Other people, and this is much rarer, but I have seen it happen, other people will guess your hypothesis and then try and throw you off by answering a completely weird way. And that's also a problem. They're not answering truthfully. They're either giving you the answer that they think you want to hear, or they're just trying to mess with you. Oh, he was talking about the Stanford prison experiment and how demand characteristics influence the results. Yeah, that was a big problem in the Stanford prison experiment. I would say it was bigger than normal too, because the way Zimbardo was running that study, it wasn't like subliminal, or it wasn't like subconscious demand characteristics or like people assuming that they wanted a certain result. Zimbardo, whether intentionally or unintentionally, was making it very obvious the result that he was looking for. So this was like demand characteristics on steroids. He made it very obvious what result he was expecting and that he would like to see evidence in support of that. This, like, generally speaking in modern studies, it's a lot more subtle. It's participants making assumptions on their own, but there's a lot of reasons the Stanford prison experiment was really problematic and its results probably aren't that great, and that is absolutely one of them. I should seek out that video after this. That might be some good evening watching. I will look for that. I'm curious. I never met Phil Zimbardo, but I did meet Phil Zimbardo's wife at a conference once. She seemed really cool. I was too scared to talk to her though. I met her in that I was introduced to her and I said, hello, it's nice to meet you. And then I was just for the rest of the time. And the Vsauce people tried to redo it, but eliminate demand characteristics as much as possible and also not be off. Yeah. That's a hard one because by not being unethical to some extent, you are reducing the environmental validity, but also you need to be ethical. You can't be a jerk. And Zimbardo went far too hard in the other direction as well. He was crazy, horrible, unethical in that study. Anyway. I wonder if they could do that. I know that they've replicated the Milgram study in, I think, 2019. They redid the Milgram study, and they were able to do it in a more ethical manner. I wonder if there's a more ethical way to do the Stanford prison experiment. These days, like, that's both more ethical and a better experimental design that is, just generally better. I'm not going to do it. I don't have that kind of money or time and I fear what people would say, but I wonder if it could be done. I have no clue how rigorous the video was, but it was very cool and their idea, and I thought it was quite clever. Yeah, I do think that's interesting. I'll definitely check it out. I will absolutely check it out. All right, but I should keep going. Okay. Disadvantages of repeated measures design. So that's not all. There's more. This isn't really a disadvantage. This is a sort of attempt to address some of the problems with repeated measures designs. People want to not have to deal with all these issues, but still get all the benefit of a repeated measures design. They still want all that delicious statistical power and to get rid of that error variance without worrying about this stuff. So one solution that some people came up with is called a matched subjects design. If you've ever heard of a twin study, that's a matched subjects design. What this is you get your participants and you measure them on everything that you think matters. Like if you're looking at a treatment for depression, you match them on how severe their depression is, when their depression started, the type of symptoms they have. You essentially try and find a whole bunch of pairs of very, very similar people. And that's why twin studies are this kind of thing. Twin studies, the idea is identical twins have very similar or even identical genetic makeups. They've had very similar experiences growing up. Their appearance is similar, so theoretically people interact with them in a similar way. They're very, very similar without being exactly the same person. So the idea here is I will find two people who are incredibly similar to each other. I'll randomly assign it so one of those people is in one condition and the other's in the other condition, and I will pretend that I've measured the same person twice. So they're trying to recreate a repeated measures design without actually measuring the same individual twice. That's a matched subjects design. When this works, it is incredible. It is... I mean, it is kind of sus, but it's also kind of great. There's a lot, I have a lot of thoughts on these match subjects. I've only seen it done once I've only stumbled on it once in the wild, and I think that one paper that I read did a really bad job of it, honestly. But I think it can be done well. And if it is done well, if you match these people on everything that matters, and somehow you figure out every variable that really matters for your study, and you match them correctly, you have all the benefits of a repeated measures design. You have that decreased error variance and all of that, and none of the costs. You don't need to worry about order effects. You don't need to worry about practice effects. That feels clever, but not rigorous. Like there's a lot of unspoken assumptions. It takes a lot of prep work. That's one of the big drawbacks. If you want to get the matching right, the amount of background research to figure out what you need to match people on is insane. The actual matching of the people is incredibly difficult and time consuming. It's a lot of time, a lot of man hours, and you don't know if it's going to work until you collect the data because you can't be sure if there's something you didn't account for. But you can tell if it worked once you collected the data. Like once you've collected the data, you can look at your standard error. You can analyze it both as an between subjects design and a repeated measures design. And if the standard error for the repeated measures design is lower than the standard error for the between subjects design, it has worked. As long as the assumptions made are clear in the results, it would be fine, but devalue the reliability of the data. Yeah, like ideally there would be some other way to do this, and there have been other clever solutions to try and deal with this problem, or at least figure out if it's an order effect or not. But I think this is a pretty clever way of doing it. But yeah, you can check to make sure that it worked. Just analyze the data with a repeated measures t-test versus a independent means t-test, and you can use that to check if you matched them correctly. Yeah. Or at least match them well enough that you're still getting the benefits. So yeah, it's not like you're just assuming that it has worked. You can check your work to see if it worked the way you thought it would. This is not like you're not going in blind with no one to check on you. But it's hard. That's the problem. It's very difficult. It takes a lot of time. And if it doesn't work, your error variance explodes. Like, it's possible that you do all this work, you go through all this effort to match all these people, but you missed out on something very, very important that you didn't match them on, and that was a key variable. At that point, the variability for your repeated measures test will be bigger than the variability for the between subjects equivalent. You've lost all the advantages of the repeated measures t-test, and you're still stuck with all of its downsides. Well, you're not stuck with all of its downsides, but you're stuck with all the downsides of a between subjects test with it's just not great. So it's kind of like, it's a very big thing to dedicate yourself to, and you will not know if all of your effort was worth it until you've already done the thing. So it's risky. It's risky, yeah. You could potentially be wasting a lot of time and money. But if it does work, it's incredible. If it does work, if you do it right, it is amazing. And it is a great solution to a lot of these. Exactly. It's high risk, high reward. Mm-hmm. So, pros and cons. The reason I don't really have a super positive view of this is, like, no two people are going to be exactly the same, but then again, I mean, sampling error, we already know we're working with samples which aren't going to be exact. So there's already some measure of error in there that we've considered acceptable. My main thing with this is the only time that I've stumbled across this in the wild, the matching was done badly, but the people who did it kind of ignored that the matching was done badly and wrote it as if the matching was done well. So I guess that one encounter has given me a bit of a bad impression of these, but they're not inherently bad. They're not inherently bad. I should seek out more match subjects designs where they actually did things right so that I don't feel as bad about it. But I would argue, Phi, that the mouse studies that you read a lot are similar to match subjects designs because you're not matching pair by pair, but you have mice that you've made it so the mice in your study in both conditions, you've artificially made it so that they're similar as possible. Like, the amount of control that you have over it, at that point, I would say it's fairly similar to a match subjects design. And you could potentially argue for using a match subjects design in that context. Anyway. So, here we go. Here's all the formulas and the equivalents across all three t-tests. You do a meta-study on the way scientists seeing one poorly done paper affects how they think about the methods within it. Or, yeah, that would be an interesting thing. Yeah, there's an effect where your first impression of something tends to be very sticky. That would be an interesting thing to do, yeah. Like, if the first study you ever see using a technique is a bad study, is that technique forever poisoned for you? I imagine actually... You know, I bet that would be the case. That seems like a very reasonable prediction that is consistent with a lot of things that we know about psychology. Yeah. Yeah, you want the mice to be as identical as possible. You're essentially creating a match subjects design in the lab. You're just basically creating a bunch of as identical as possible mice, which is not something that you can do in psychology. That is not something that they would allow us to do in psychology. But I think you could argue that it's kind of like a pseudo match subjects design. Anyway, and here's our table. You have your sample data for each type of t-test. You have the hypothesized population parameter for all three types of t-test. You've got your variance formulas for each type of t-test. You've got your estimate standard error for each type of t-test. And you've got the t formula for each type of t-test there. Well, as Tom from the channel Explosions and Fire says, the most important part of chemistry is to be able to hold grudges. The sheer amount of science that is driven by spite is mind-blowing. My advisor's entire career started because of spite. Or, like, her area of expertise was solely based on spite. She had one argument with somebody. She was really mad. She thought they were so wrong. And she grew an incredibly successful career solely out of spite over that argument. OP study guide. Yeah, I think this is really handy. I think it's really nice to just have this kind of crosswalk between them. If you have experience with some chemical and it's just miserable, yeah, hold a grudge against that chemical forever. That also makes sense. Spite fills me to the point I have forgotten who I'm spiting. Feels like that for me sometimes too, I'm not gonna lie. I've gotten to the point where I have spite over certain theories, but I forget who put the theories forward, so my spite is directed at the theory alone. It's kind of stupid. But I think that's probably a better way to go about it, honestly. Like, I don't have negative feelings towards the researcher themselves, I just have negative feelings towards the theory. Half the papers, if they were honestly titled, would be called "This Person is Wrong After Years of Work, I Can Finally Prove It." Oh my gosh. I've been collecting over the years, and I haven't saved them in any systematic way, though I really should. I've been collecting over the years series of papers titles that are replying to one another, where the passive aggression in the titles of the papers is palpable. It is my favorite thing, just finding people throwing shade at each other via paper titles and abstracts. It's so funny. Spiting yourself is a great way to generate infinite motivation. True. I spent months making shitty radiation shielding despite a multi-million-dollar company that was selling rad shielding that was really expensive. Better make sure it works. But like I totally get that. I understand. All right, I have one more slide. Made a good video, to be honest. Yeah. At this point, I'm pretty sure science itself depends on spite. I don't think all of science depends on spite, but I definitely think a bigger portion of science than most people would predict does depend on spite. Passion is absolutely in there as well. Like passion and curiosity and just love of the game is a big factor as well. But spite is also a factor. I just remembered something. I think one of the reasons I was able to complete my PhD was spite. But that's a story for another time. I'll tell that story another time. The biggest spite-driven accomplishment of my life. I don't think the person that I was mad at even remembers that I exist. But I remember them. That's not a healthy way to live your life. But it was very motivating, so I'll give it that. Okay, last slide. A bit of review. I know this is kind of a throwback. It's Suika game, which I love. Maybe I should play Suika game on stream sometime. Anyway. Oh, but I have it on Switch, which is bad for my carpal tunnel. I will sacrifice my wrist for the sake of gaming. Anyway. We need to study on whether scientists are massively more spiteful than the average population. I don't think we're any more spiteful than the general population. I don't think we are, but I think human beings in general are just spiteful. It's free online? Then I can play it online! Okay, I'll do that. Maybe one day I will play Suika game on stream. Perfect. Beautiful. Love it. I would like to do that someday. Thank you. This is good. You can emulate it on PC, I bet. Yeah. One way or another, I'll find a way to play it on PC so I don't destroy my wrist. Even if it's not for stream, even if it's just for my own personal enjoyment. Okay. So, I want to compare my score in Suika game to the average player. I have my score, and I have the population mean and standard deviation. Which test do I use? Oh, you're playing it right now on iOS? Nice. Nice. All right, yeah. Which test am I going to use? I'm not going to bother to start a poll on this one. So I've got the population mean and the population standard deviation. Our options are the independent samples t-test, the single sample t-test, the repeated measures t-test, and the z-test. Single sample is close. You are close. You are very much on the right track. I guess this is kind of unintentionally a trick question, but not really. It's the z-test. You are correct. Yes. Yes. In this case, the key to knowing that it's the z-test is I also have the population standard deviation. If I didn't have that, it would be the one sample t. But because I do have that, it is the z. Yeah. Exactly. It is z. It is the z-test. So I guess, like, the reason I was like, this is kind of a trick question, even though I didn't intend it to be, is like, I've been talking about t-tests for the past 3 lectures, and suddenly I hit you with a z-test, but yeah, it's z, it's Syzygy, it's Syzygy. I'm still so scared. I hope I'm pronouncing her name right. Z, please forgive me if I'm not. Syzygy is such a fun word, though. Syzygy? Syzygy. You'd think I could pronounce my own genmate's name, but I just go for Z. I can pronounce Altair. Anyway, there we go. There is our repeated measures or dependent means or paired samples, whatever you want to call it, t-test. Anything that you would like me to clear up? Any questions, comments, things like that? I think I got it. Yay! Yeah, my goal is to pronounce as many names correctly as I possibly can. I just, looking at it, I wouldn't try Syzygy. I know every time I try and type out Syzygy, I can't type it right. I can't. I have to Google Z Altair VTuber, and that's how I figure out how to spell syzygy. It's embarrassing. I'll learn it eventually, though. Clearly, I should just do an entire stream trying to remember how to spell syzygy, but that's not a good way to study. That's just cramming at that point. Ah. Don't tell Z. Don't tell Z. This is my shameful secret. Oh. All right, yeah. Any last things before I duck out? It's almost time to feed the beast. The beast is napping, so I do have time, but it's almost time to feed the beast. And you're a good beast, aren't you? He's such a good creature. He's doing good naps right now. I wish I was as good as naps, is the beast. I see what you wrote. I think that's my sign to leave. Astral's kicking me out of my own stream. Oh, thank you all so much for coming. I had a lot of fun. Thank you all so, so much. Next time we get to start talking about ANOVA. Yeah, thank you, everyone. Thank you for coming. All right, take care, everyone. I will see you next week, or maybe this weekend if the drawing bug gets me. Maybe I'll stream some drawing this weekend. We'll see. But either way, good night, everyone. Good night, Xenotime. Good night, Astral Atrophos. Good night, Heraday. Good night, Mori. Good night, Phi. Good night, everyone. I think that should be everybody who's here. I don't know for sure. But can't even ban I in chat because, like, I eat tacos. Yeah, I can't. Good Nacht. Oyasumi. Oyasumi nasai. Or whatever. Okay, anyway. Night-night. Bye-bye.